Hello, so today we will see how to do a numerical based on balancing of multi-cylinder inline engine. But here the specialty or the importance is this firing order will be specified. That means in multi-cylinder engines, as we know, the firing or the spark or ignition is not given all at once. It is there is a specific order for ignition. So we will see how to do a problem or a numerical in which the firing order of a multi-cylinder inline engine is specific. So we know what is firing order. Just to mention what is firing order, let's consider this five-cylinder engine. A 3D view, isometric view of five-cylinder engine is there. A 3D view is there. We see 1, 2, 3, 4, 5, 6. So five cylinders are there. Five, not six, five cylinders are there. And what happens if we suppose to consider all of these pistons are at TDC, and if we give firing or spark to every cylinder at once, what happens is all of those five cylinders will go down. Not cylinders, pistons will go down, creating a torque on the crankshaft. And again, all of those will come up, creating an upward torque on the crankshaft. What happens is if all of these engines, all the cylinders are fired at once or all the pistons move in same direction all the time, what will happen is there will be huge vibrations in the engines which will be totally unbalanced, and that can cause structural damage to the engine. So to avoid that and to avoid additional torque or damage or vibrations in the engine, what we do is we create a firing order that maintains this vibrations. We cannot completely avoid vibrations in a reciprocating engine, but still internal combustion engines, there is a firing order mentioned. So in numericals there will be a firing order. So we will see how to do a numerical. First, let me see what is done. We were provided with a four-stroke, five-cylinder inline engine. So four strokes are there, five-cylinder inline engine is there, and the firing order is mentioned as 1 4 5 3 2 1. That means first cylinder one will be fired, then four will be fired, then 5 will be fired, then 3, 2, then again that cycle continues. 1 4 5 3 2, 1 4 5 3 2, that cycle continues. Or not all will be fired at once. So that is what is the firing order is. This firing order has a great importance in while we draw primary and secondary force polygons and couple polygons. So the center lines of the cylinders are spaced at equal intervals of 15 centimeters. So let us draw the planar diagram. I'm drawing the planar diagram. So five engines are there and all are equally spaced. So 1, 3, 4, and 5. Yeah. So we can name it as 1, 2, 3, 4. 1, 2, 3, 4, 5 cylinders, 5 engines, and all are equally spaced. So all are equally spaced at an interval of 15 centimeter. That means 0.15 meters, 0.15 meters, 0.15 meters, and 0.15 meters. So that will be the planar diagram, and some values are reciprocating parts per cylinder is 1.5 kilogram. So that means M is given as 1.5 kilogram, and engine rotates at sorry, the stroke of the piston stroke is 10 cm. So stroke means, if you remember from thermal engineering, stroke means the travel that piston makes from TDC to BDC. That is known as stroke. When piston reciprocate comes from TDC to BDC, which is the maximum it can go, the travel that piston makes from top to the bottom dead center is known as stroke length or stroke. So piston stroke or stroke length. So I'm calling it as S. So that is given as 10 centimeter. So it will be 0.1 meter, and the importance of the stroke length is nothing but radius of crank R will be equal to S by 2. Radius of this crank will be, this radius will be equal to the half of the stroke length. So that will be equal to 0.1 divided by 2, that will be equal to 0.05 meters. So instead of giving R, they have given stroke length. And length of the cutting rod is given. Cutting rod is given as 1.7. So L is equal to, or taking the other L to avoid confusion with reference plane, is equal to 17.5 centimeter or 0.175 meters. And why this L is given, and stroke length and cutting rod length is given to find out the obliquity ratio, that is N dash is equal to L by R. So that will be equal to 0.175 divided by 0.05, and you will get it as 3.5 meter, 3.5, not meters. There will be meters and meters will be cancelled. Ratio will be unitless. So obliquity ratio is 3.5, and speed of the engine is given in RPM. Engine rotates at 600 RPM. So speed is mentioned. So we can write N is equal to 600 RPM. We are not concerned with RPM. What we require is omega, that is angular speed in radians per second. That will be 2 pi times N by 60. And if you substitute 600 for N, you will get 62.85 radians per second as omega. So omega is 62.85. So that is the values that are given. So this is a four-stroke engine. So now that four-stroke has an important, because we know in a four-stroke engine, first stroke will be suction stroke. So if this is an engine and this piston moves, okay, otherwise we can consider when it is to four stroke, then first stroke it will move from TDC to BDC for suction, and that will cover a crank of 180-degree movement of crank. You can see it here. This crank will travel from straight position to the lowest position. So it will be 180 travel. Second again stroke BDC to TDC, that will be for compression. That will again create 180. So like that, a total of third again will be TDC to BDC. That will be a power stroke or expansion stroke. Again 180-degree travel will take. So, and fourth one, last exhaust stroke, will be BDC to TDC. That will create a another 180 travel. So 720 degrees it will travel, or 360 into 720 degrees travel for four-stroke engine. So that will be for four-stroke engine, and since it is a five-cylinder engine, that means this cylinder will be fired at a instant where all the cranks will be at equal distance to each other, and total travel is 720. So each of these cranks will be at an angle which is total travel divided by 5. Since it is a five-cylinder engine, since it is five-cylinder engine and a four-stroke five-cylinder engine or five-cylinder four-stroke engine, you can have five-cylinder four-stroke engine. The angle between two cranks at an instance will be 720, which is the total stroke of four stroke. So the total angle travel of 4-stroke divided by the total number of engines cylinders, that is 5. So 720 divided by 5, you will get as 144 degree. So each crank will be at an angle 140 degree with each other. So now it is time to construct the table consisting of reference plane and all. So it is not mentioned to take anything as reference plane. So it is our choice to take which is as reference plane. So in order to avoid the larger number of negatives or anything, because it is an odd number of cylinders, it is better to take 3 as the reference plane. Then you will get equal, opposite and negative and positives. You can take 1 as reference plane, 2 as reference plane, but it is better to take 3. So I am fixing 3 as the reference plane. So all the values of lengths right of that will be positive and that left will be negative. So 3 will be our reference plane. Now we will take up how to construct the table. So let's now construct the table. We know the table from the numerical of inline engine. The table remains the same, only the firing order is mentioned. So first name the planes 1, 2, 3, 4, 5, since it is 5 cylinders, and we have already named 3 as our reference plane. So and all the masses are equal to 1.5 kilogram. So 1.5, 1.5, 1.5, 1.5 and 1.5. And since this is a reference plane, distance from reference plane for 3 will be equal to 0 and the couple will be also equal to 0. Let's fix that so that reference plane is complete there. And radius of all the masses rotating is stroke length is 10 centimeters, so radius is s by 2. That will be 5 centimeter or 0.05 meters. So radius will be 0.05. Yeah, and all the centrifugal force will be same because radius and the mass are same. So 1.5 into 0.05 will give you 0.075. So that will be 0.075. In most of the firing order questions, this will be the same criteria. Even if it is 4 cylinder, 5 cylinder, or 6 cylinder, most of the cases the masses and the radius will be same for inline engine because most of the cranks will be of same length of cutting rod and same stroke length. Then only it will be balanced. You cannot have cranks in inline engines with different cutting rod lengths and different stroke. In most of the cases, it will not be the case. There may be exceptions, but in numericals, normally we see that also all the cases the masses and the radius of cranks will be same, or other words, stroke length will be same, and distance from the reference plane. Let's see. 3 is our reference plane, so distance from 3 to 1 is negative 0.15 plus 0.15. So that will be negative 0.3. So negative 0.3 and 2 will be negative 0.15 and 3 is our reference plane and this will be positive 0.15 and the last one will be outer crank will be 0.3 and the couple MRL, which is this centrifugal force times distance, that will get as 0.022 for the first one, negative 0.011, and for the third one 0.1011 and 0.022. Now the crank position. So this is the time when it really matters. So we know total for a 4-stroke engine there will be 720 travel, and for a 5-cylinder engine at an instant the angle between two cranks will be equally divided between all the cranks of the total travel. So total travel is 720 and 5 cylinders will have 720 divided by 5, that is 144. So but the firing order is given, so we know the firing order. Firing order Firing order is given as 1, 4, 5, 3, 2, 1. So this firing order plays an important role in determining the angular position of the crank. So if you fix, it is normally best to fix first mass as 0 or the horizontal. So the crank position of that will be 0. And we already know the successive cranks will be at 144 degree. So first crank is 0. The next crank that comes into the firing order is 4. So after 1, 4 will be fired. So angular position between 1 and 4 is 144. Not 1 and 2. Since the firing order is mentioned, the angular position of the first two cranks is 144. And 144 we got as 720 divided by the number of cylinders. So 1 and 4, the angle will be 144. So if 1 is fixed as 0, the fourth crank will have an angular position of 144 degree with respect to the horizontal. And angular position between 4 and 5 will be another 144. So if we can mention it as theta 1 is equal to 0, theta 4 will be 144 degree, and theta 5 will be 0 plus 144 plus 144. That will be 144 plus 144. Since we are taking angle with respect to 0 at 1, that is horizontal. So 144 plus 144 will be 288 degree. Next that comes in is third one, 14532. Again, third one with 5 is 144, but with 1 is this 288 plus 144, or 144 plus 144 plus 144. So theta 3 will be 288 plus another 144, that will be equal to 432 degrees. And again next that comes is second crank. So between 3 and 2, that will be 144. So that means 432 plus 144 will be the angular position of second crank. That means 432 plus 144, that will give you 576 degrees. So let's mark that in the column. So 1 is 0, 4 is 144, 2 is 576, and 3 is 432, and 5 is 288. So we see that it is 576. So we cannot mark an angle beyond 360 in a circular diagram or a 2D diagram. So what we do is, instead of 576, when we draw it, we don't actually have to take 576. We have to take only 576 minus 360. That will be equal to 216 degree. Similarly, 432 may be taken as 432 minus 360. That will be equal to 772 degree. Okay, now we got primary crank position, and we know secondary crank position will be at 2 theta. So 0 will be 0, and we should not take double of this 216. We should take the double of the original crank position, that is 576. We should not double this one. This is just for drawing purpose, we are taking 260. Actual position is 576. So double of 576 will be 2 theta will be 1152, and that for drawing that 1152 we should take 1152 times 360 is multiple, nearest multiple. So if you consider 360, then 1152 will come as 72 degrees, because 1152 divided by 360, sorry, 1152 divided by 360 will give you 32. So 32 times full rotation will happen. After that is 72. So we can draw it as 72 degrees. And 432's double will be 864, and the angular position of 864 will be actually 144. You can divide 864 by 360, and the remainder will be the 144. Similarly here, 1152 divided by 360, the remainder will be 720. And next one is 288 degree, and last one will be 576 degree. 288 times 2, that is 576. Again 576 divided by 360, the remainder will be 216 degree. So this is the table. Now we should move on to drawing the angular diagram of this figure. So we can fix first mass as the horizontal. So I am going to fix the first mass as horizontal here, and second mass, or the next mass of, comes in firing order, is 4, and 4 is at a primary angle of 140. So we are drawing primary. Okay, we should name it primary crank positions. We are drawing primary crank position. So first mass, and 1 and 4 is having an angle of 144 degree. So place your protractor and take a 144, come around here. So draw a 144 from there. That will be your fourth mass. And next that comes in is 145. 5 is at an angle of 288. So 288 will be 270 plus 18. So 270 will be the line vertical to this one with respect to 1. So an 270 plus an 18 you should take. So you place a protractor and an 18 from this 270 line, that will be here to here. So that will be mass 5. 5. And next one will be 1453. Third one is at an angle 72 432 degree actually, but we can take it as 72 because 432 will come as 360 plus another 72. So 432 will be 360 times then one revolution after that 72. So place a protractor over here and mark 72. That will be our 432. That will be third one, and next one will be second one. Second one is at an angle 216 degrees. Actually it is 576. So 2 times 360 plus another 216. So 216 will be 180 plus 46. So 180 plus 36. So already there is a 180. Take a 36 from 90 or a 36 from horizontal. Around here. Yeah. There is no scaling required to draw this diagram, but you should draw this diagram accurately so that we can trace the lines from this diagram easily to mark the second one. So let's mark the angles. This one will be 72. This one will be 144. This one is, second one is 216. And the last one of this one will be 288 degrees. So if you know the angular positions of the crank correctly, then it is easy to draw the force polygon. So force polygon should be drawn according to the firing order. So primary force polygon. Primary force polygon. So we, in the question it is asked to find out, determine the value of maximum primary and secondary unbalanced forces and couples about the central plane. Because central plane is 3, that's why we have taken it as reference plane. I forgot to mention that because it is asked to find out about the central plane. Central plane is 3, that's why we are taking 3 as the reference plane. So to find maximum primary and secondary unbalanced forces and couples, we need to draw the force polygon and couple polygon for primary and secondary crank position. So primary crank position, the force is for the first mass is taken as horizontal. Force is 0.75. It is equal for all. So taking 0.75. So for drawing primary force polygon, take a horizontal line, scale it and place it at 0.75. You can scale it as much as you like. So 0.75 as the first force. 0.075, sorry, 0.075. So that will be the first force of the primary. Now you should draw according to the firing order. Let's name it O, and this will be 1. The firing order is 1, 4, 5, 3, 2, 1. So after 1, you should draw 4. And you should not consider the angle. If you want, you can consider it as 144. Otherwise, if you have this diagram, then it is easy to draw. Just use a scale. Try to align a rolling scale. Try to align it with the 4. And if it is properly aligned, move it to the this position so that you can superimpose that. So that will give you the crank position of fourth one. So I am drawing it to an angle. That is the easiest way to draw it. So that will be 4. That will be another 0.5. And the next one is after 4 it is 5. So fifth one again you just place a scale that is parallel to 5 or a set square and a scale combination. What a rolling scale if you have, that will help, and keep it to at the end of the fourth one. So it will be somewhere here. So the line will be actually like this, and you have to scale it to 0.075, 0.075, and again 145. Next firing order that comes in is 3. So again you can take the angle or you can take this scale method tracing. This is the most easiest method. If you take the angle, it may be a little time consuming, or if you want to take an angle, take the angles of the primary crank position in the external angle. So this will be at an angle. So that will be at this position. That will be, this is 5, this is 3. This is again all forces are, if you see the table, all forces are 0.075. So if you scale it, it will be equal lengths. And the final position is 2. So take the parallel of 2 or take the angles from the primary. I am showing this method because this is the easiest method. If you have this diagram drawn perfectly, then this will be the easiest method. So align it to 3. Yeah. And exactly, since all the angles are same, you will exactly get a closing figure like this, a star or a penta star. You will get it like that. And since force polygon is closing, this 0 will again be 0 will again be 2. All, so since the force polygon is closing, there is no open side. That means primary or no unbalanced primary forces. There are no primary forces that are unbalanced because the force polygon of primary crank position is closing. So now we should consider how to draw the primary couple diagram. So now let's draw primary couple diagram. Primary couple diagram to find if there are any primary couples which are unbalanced. Primary couple polygon. Polygon. Yeah. So we know the couples, that is negative 0.22, 0.1, 0.011, that is also negative. Then third one does not have a couple. Then fourth one and fifth one. So and the angles are already mentioned for the primary crank position. So this will be the primary crank position. So first we should take horizontal as negative 0.22, 0.022. So taking negative 0.022 at a proper scale at an appropriate scale 0.22, then that will be 0, and to mark it as 1 because that will be 0.022 negative direction. Now the according to the firing order only this should be drawn also. So after 1 that comes 4. Again you can take a 44 from inside of, because this is negative, a 44 from here, 144 degree from there, or you can just simply use the tracing method or the superposition method of 4 like we did earlier. Place a scale to the fourth crank, or rolling scale to the fourth crank, and trace it towards the end of this one. And this should be 0.011. Again it should be negative. So you can the polygon with side, that is 0.11. Yeah, this is 0.22, that is 0.011 negative. And third one next comes is fifth one, 145. Fifth one is at an angle 288. So you can draw either that fifth one at 288, or you can just simply again use the same method of tracing. So I'm going to trace that to here, and that side should be, for 5 the crank is at 0.22, 0.022. So a line similar to of same length as the first one. And after 5, 1, 4, 5, 3. But 3 there is a problem, that is no couple is there because 3 is the reference plane. So 3 you should not draw because it is 0. But next one is 2. 2 is having a couple of negative 11, and that will be at an angle 216. So either you can do that, or you can just simply use the rolling scale again and use the same method. This method is applicable for all the balancing problems. You don't have to measure the angle. You can just simply use the crank position diagram or the mass angular position diagram to sketch out the forces. So it will be somewhere around, this will be the angle you will get if you draw it correctly. And then length of the side should be, for the second one, negative 0.11. So it will be smaller one, 0.11. So this is 0.022, and this is the fourth one, 0.011. This is fifth one, 0.022, and third one is 0, and the second one is 0.11. And this polygon is not closing, that means there is a unbalanced force there. Since this polygon is not closing after 1, 5, 4, 3, 2, 1 firing order, so that means there is an unbalanced force acting on, which is of the length from here to here. And if you do it properly, you will get that unbalanced couple as length as, just a second, let me see. You will get this length equal to unbalanced MRL. From MRL diagram we are getting it as unbalanced MRL component, you will get it as 0.016. Yeah, 0.0165 kilogram meter square you will get. But for unbalanced couple will be, we know the primary unbalanced couple equation is primary couple equation is primary couple, that is MRL omega square cos theta is the primary couple. MRL omega square cos theta is the primary force, and apply and multiplying that with length you will get, and maximum condition is cos theta equal to 1. So maximum couple will be maximum couple CP will be C for couple and P for primary. Yesterday we have learned it. That is MRL into omega square. That will be the maximum condition. So what we got here is actually MRL only. We have not taken omega square. So primary unbalanced couple, when you write it as answer, unbalanced couple, you should multiply this with omega square 0.0165 times omega square, and the answer you will get is omega square is 62.85. So that will be answer you will get as 65.18 Newton meter couple. This is the primary unbalanced couple. Primary force, there is no unbalanced force, but in primary couple there is an unbalanced component, that is 65.18 Newton meter. Now we should use the same principles to draw the secondary force polygon, but you should change the crank angle to the secondary polygon, secondary crank position according to the angle segment. We will see how it is done. Okay. Now let's see how the secondary forces and couples are drawn. For that you have to draw secondary crank position. Secondary crank position. So we know the secondary cranks are at an angle. If you notice something here, see, all the angles are there. There is a 72 here, there is a 72 here, there is a 216 here, there is a 216 here, there is a 208 here, 88 here, 144. All the angles are there. So if you have your primary crank position, that will be similar, only the order will be different. We will see it. First, let us fix horizontal line as 1. First horizontal crank as 1, and second crank that comes in is 4, and 4 is at an angle 216 degree. So take a 216. 216 will be 180 plus another 36. Somewhere around here. So that will be secondary crank of 4. And next there comes in firing order is 5. So that is at a, okay. Sorry. 5 is at a 216, 4 is at a 288. Sorry. So this is actually 5 at a 216. So this will be 5, not 4. That will be 5 at a 216. 4 is actually at 288. So 288 will be 180 plus 270 plus an 18. So you can take 90 plus an 18, somewhere around here. So that will be 288. That will be the fourth crank. And 145, 3 is at 72 degrees. So take a 72. So that will be 3, crank position 3. And the second crank is at an angle, sorry, 2 is at 72, 3 will be at 144. Sorry, again my mistake. 2 is at 72, 3 will be at 144. So this will be 2, not 3. So 2, 3 will be at 144. So 144. This will be the angular crank position of 3. So if you notice it here, this was the same diagram for primary crank also, but this number is changing. You see, for primary crank position, that 144 degree was occupied by the fourth plane, whereas in secondary crank position, 144 is occupied by the third plane. And 72 was occupied by the third one, whereas in secondary crank, 2 is occupied by the 72 is occupied by 2. Similarly, 216 is now occupied by fifth one, whereas in primary it was occupied by 2. Similarly, all the crank positions are same, only the name is different. So this is the crank position diagram. Now we should draw similar to the primary force, secondary force polygon to check whether there is any secondary unbalanced force. So secondary force diagram, again this should be drawn according to the firing order. So secondary for force remains the same, only the angle is difference. So force remains 0.075 itself. So drawing 0.075 as the horizontal, that will be 0.0751 and 0. And according to the firing order, the next that comes in is 4. So you should draw a 4. But here the 4 is not at 144. 4 is here according to the secondary crank position. So align your rolling scale with the fourth crank in the secondary crank position. Draw it from here. So this will be 4. All are of equal lengths of 0.75 because all the forces are same. Only the angles remains a little different. 4 will be like that. And next that comes in the firing order is okay, sorry, 4 will remain. Okay, we will check it. Okay, 4 will not be upward, 4 is at 288, so the 4 will be actually a downward line, not my mistake. This is actually not, so this is 4, not that one. Okay, that is the fourth line. So this is 1, and this will be 4. And the next in firing order is 5. So 5 is at an angle 216, or you can make it from this one. So that will be at an angle. Yeah, take the ruler, align it properly with the fifth position. So that will be fifth line. And that will be 5, 1, 4, 5. Next comes 3 in the firing order. So third crank, which is at 144. Again, use a scale or ruler, a rolling scale. Align your rolling scale with the third position. Or you can take the angle in a protractor. That is perfectly all right. If your crank position diagram is in another page, you can take it. Yeah. So that will be like that. And 3 and 2 will be, and the last one will be 2 firing order. So this is our 3, and 3, if you do it correctly, then it will actually close out at the making a pentagon. So there will not be any unbalanced secondary forces. So let's see if it is closing. If you have drawn it to accurate scaling and everything else, it should close. Yeah, it is closing. My drawing is not that much accurate. Since the length are not taken to the scale, you should take the length to the scale, then you will perfectly align these edges with each other. So we can close it and make it a, so this one will be 2 or 0. So since the polygon is closed by itself by taking the values, so no unbalanced secondary forces. No unbalanced secondary forces because the polygon is closing. If there is an open polygon, then the closing side will be unbalanced. So this is the secondary force polygon. Okay, now we should draw finally the secondary couple polygon. Secondary couple polygon to find out if there is any secondary couple that is unbalanced. So secondary couple polygon, like we draw the primary couple polygon, we should take these couple values and draw with the angles of the secondary triangle. So taking first one as negative 0.0.22, so that is our negative 0.22. Let me draw it a little top because it will be a diagram downwards. That will be a 0 1, and couple will be 0.022. It is negative, so it is taken from left to right. And the second one in the firing order is fourth one, and the fourth couple is 0.11, 0.011 positive. So you should get a couple equal to 0.011 scaled but aligned properly with the position of 4, either by taking angle at that, or you can align it with the scale. So that will be the line, and you should scale it to 0.11. That will be the half of the first one. So I am not scaling, you should be doing it with a proper scale. So 0.011, that is fourth one, fourth couple. And after 4, the firing order, it comes 5. 5 is having a couple of 0.22, and it is an angle of 216 secondary angle. You can use that angle, or you can use that again a ruler to rolling scale to align it. So align it properly. So I am just going to mark that and draw a line that is equal to 0.22. That is the first line. So scale it to 0.22. It will be like that, somewhere around there. So it will be 5, 0.022. And after 5, the firing order 3, 3 is 0, because a couple of 3 0 reference plane is taken as 3. Then you should to take 2, that is 0.11. So 2. So aligning with 2, so you should get an angle like this. Let's just erase that 0.22, so get a proper view of that. Yeah. So it will be like that, and you should scale it to 0.11, because the couple of the representing point 2 is actually negative 0.11. So since it is negative, you should get a secondary couple polygon on downward direction, because it is taken as negative. So you should take it as downwards. Because this will be the positive 0.22 side of 2. So since it is negative, you should take it downward direction only. So that will be our 2, and 3 is 0. So you will get a polygon like this, and the ends are not closing. So the closing side will give you the unbalanced force. So taking another color. Okay. So this will be your, okay, no, this is not a line. So this will be your unbalanced secondary couple. Unbalanced secondary couple. There is an unbalanced, and the secondary couple, we know it as secondary is M R L omega square cos 2 theta divided by n. But for maximum secondary couple, we are asked to find out in the question. We are asked to find out maximum primary and maximum secondary couple. Maximum primary, maximum secondary couple. So for maximum condition, cos 2 theta will be equal to 1. So what you will get is MRL omega square divided by n. So we got this as MRL of the secondary couple. So we should multiply that with MRL value with omega square divided by n as the secondary couple. So if you do it properly, you will get, this is you will get it as 0.0517. You will get this length as 0.0. After scaling you will get it. So that times, so secondary unbalanced, secondary couple will be 0.0517 times omega square divided by n. And if you do it correctly, omega square is 62.85 and n is 3.5. Answer you should get it as 58.3 Newton meter. So this will be the secondary unbalanced couple. So we have solved the entire thing. Find out primary forces are not unbalanced. It is a completely balanced. Primary couple is unbalanced. We have found out primary unbalanced couple, and we have drawn secondary force polygon. It was perfectly balanced, but the secondary couple polygon is not balanced. So we found out the length and multiply it with omega square. You should not forget to multiply with omega square by n for the secondary couple and omega square with the primary couple. Otherwise, your answer will be unfinished. So this completes this problem. And if it is for a 6-cylinder engine, only thing you have to change is you should change the two. If it is a 6-cylinder 4-stroke engine, the total angle will be 720, and each four of the cranks will be at 720 divided by 6. If it is a 4-cylinder engine, you can change this to 4 and get the appropriate angle. All the others remain same. Only thing is this angle will change accordingly to the number of cylinders. Thank you.